Welcome back after lunch for the afternoon track. The first talk that we have now is by Professor Nikhil Srivastava from IIIT-Bangalore. And he's going to be speaking on the topic Bipartite Ramanujan graphs of every degree.
So thanks a lot for inviting me. So this is about bipartite Ramanujan graphs of all degrees. It's joint work with Adam Marcus and Dan Spielman. Can everybody hear me? Okay. And feel free to stop me at any point because, you know, this talk is way shorter than 1 hour. So really stop me if you don't understand something. Okay. So the talk is about expander graphs, and an expander graph is a sparse regular graph which is very well connected. Okay, so regular means that every vertex has the same number of neighbors, and sparse means that this number is small, like 3 or 5. It's a constant. So the degree is small, and it's well connected. Okay, so there are many ways of defining this well connectedness, but the way I like to think of it is that an expander is a sparse, well connected regular graph which is sort of behaves like a random graph. Okay, so you can define this combinatorially. You can say that every set of vertices has many outgoing edges, so it has many neighbors. So that's one notion of well-connectedness. You can define it probabilistically. So you can say that a graph is well-connected if random walk on the graph mixes quickly. And then there are algebraic geometric definitions, which we'll get to later. But basically, these graphs are extremely useful. They're useful in network routing. They're useful in complexity theory and making pseudorandom generators. They're useful in making error correcting codes, and they're really useful family of examples in various areas of mathematics like metric embeddings. Okay, and if you've never seen an expander, let me just show you some pictures. The graphs on the left are expanders. So this is the Peterson graph, and this is a random graph on some number of vertices. And these are very well connected, and they satisfy any reasonable notion of expansion that you would be interested in. And these are not expanders under any reasonable notion. Okay, so it's easy to cut this into 2 pieces by cutting very few edges. It's not a well-connected graph. It's also clearly not random in any sense. Okay. Okay, so let me get more specific. So the definition of expansion I'm going to be interested in this talk is a spectral definition. Okay. So to define a spectral notion of expansion, I'm going to need to look at the adjacency matrix of a graph. So suppose G is a deregular graph on n vertices. Then its adjacency matrix is an n by n symmetric matrix with zeros and ones, which we all know. And because it's symmetric, it has n real eigenvalues, which I'm going to call lambda 1 through lambda n in descending order. Okay. Now, it turns out there are some very generic facts about these eigenvalues that hold for all graphs. Okay, so the first thing you might discover is that for any deregular graph, the number d is always an eigenvalue, and it's the largest eigenvalue. Okay, so it's easy to check that a times the all ones vector is just equal to the d times all one vector. This is saying is that the row sums are all equal to d, which is just saying that each vertex has d neighbors. Okay, so every deregular graph has a top eigenvalue of d. Certainly, and you can prove that this is the largest one. There are no eigenvalues bigger than this. And then a similarly easy fact is that if D is a bipartite graph, okay, then the eigenvalues are actually symmetric about 0. So if lambda is an eigenvalue, then minus lambda is also an eigenvalue. This is a nice exercise that you can do if you don't know this fact. And so this implies that if D is bipartite, then minus D is always an eigenvalue as well. Okay. So all graphs have eigenvalues of d, and if bipartite, minus d. And so these don't really tell you much about the graph because all graphs have these properties. So I'm going to call these the trivial eigenvalues. Okay. Any questions about this? Okay. Okay. So the spectral expansion is defined in terms of the remaining eigenvalues. Okay. So here's the definition: a graph G is a good expander. Okay. If all of its non-trivial eigenvalues are small. So I just told you that there's always a d eigenvalue, and if it's bipartite, a minus d eigenvalue, and the rest of the eigenvalues are somewhere in between. And the definition is that G is a good expander if the eigenvalues are really close to 0. Okay. So here's a sort of canonical example of, in some sense, the best expanders. If I look at the complete graph on d vertices, you can check that all of the non-zero eigenvalues are actually equal to 0. Okay. So that's a really good expander, and that makes sense because it's really well connected. And the complete bipartite graph also has all non-trivial eigenvalues equal to 0. So the best you can do is just have everything else be 0. But what's interesting and useful in this area is not just to have one example of an expander, but to have an infinite family. Okay, so what we're interested in is infinite families of expanders where n goes to infinity, so the number of vertices gets bigger and bigger, but d remains fixed. Okay, so here if I let d go to infinity, I get a bunch of expanders, but then the degree is also going to infinity. It's not a sparse graph. So what I want is that the degree is fixed, but the number of vertices go to infinity, and I still want this property. Okay. Okay, so it's pretty easy to check that you cannot have an infinite sequence of graphs which are d-regular and which have all the non-trivial eigenvalues equal to 0. Okay, so you just cannot replicate this behavior for the small examples. And actually, it's very well understood how well you can do. Okay, so this is a result of Allor and Bopanna from 1986. And what they showed is that if you give for any infinite sequence of graphs, it must contain a graph with a non-trivial eigenvalue that's arbitrarily close to this number 2 square root d minus 1. Okay. So for any infinite sequence of graphs, I cannot concentrate the eigenvalues in any interval smaller than 2 square root d minus 1. This is an important number. Okay. So this is the limit of how well you can hope to do. And this is what's called a Ramanujan graph. So Ramanujan graph is a d-regular graph if all of its non-trivial eigenvalues are at most 2 square root d minus 1. So this is the best possible spectral expander. Okay? Optimal spectral expander is called Ramanujan graph. And sort of a fantastic thing about Ramanujan graphs is that they actually exist. So infinite sequences of Ramanujan graphs actually exist. So there's this beautiful work of Margulis and Lubatsky, Philip Sarnak from 1988, who showed that whenever d is equal to p plus 1, where p is a prime number, there's an infinite sequence of Ramanujan graphs of degree d. Okay, I'll say a little bit more about that in a moment, but they gave an explicit example of graphs that actually meet this bound. So it's tight. And more recently, and somehow more generically, Friedman showed that if you take a random d-regular graph, so if you just take a union of d matchings, d random matchings, then it's almost Ramanujan. What that means is that its eigenvalues lie in the interval 2 square root d minus 1 plus epsilon, where epsilon is something very small. Okay? But I'm actually interested in exactly Ramanujan. I'm interested in getting exactly this bound. Okay, so let me say a little bit more about this. So what did they prove? Lubatsky, Philip Sarnak, and Margulis. So they proved that if you have two primes p and q, which are different and congruent to 1 mod 4, then there's a p plus 1 regular graph. Okay, so the degree is p plus 1, d is equal to p plus 1. And the number of vertices is q. And all the eigenvalues are at most 2 square root p, which is 2 square root d minus 1, which is Ramanujan, which is optimal. Because you can get infinitely many pairs of p and q that are different with this property, you can let q go to infinity, and you get an infinite sequence of graphs like this. And the proof is, well, the graphs they came up with were Cayley graphs of PSL2 of z mod qz. So if you don't know what that is, I'm not going to really tell you, but it's some sort of it's some matrix group. The way they actually analyze the eigenvalues of these graphs is based on something which actually came out of Ramanujan's mathematics. It's based on a lower bound on the number of on the number of solutions of this equality. So it's some quadratic form in x1, x2, x3, and x4. So okay, as was mentioned earlier, Jacobi showed that it's possible to write certain numbers as sums of 4 squares, right? And he figured out how many ways there are as well. So this is some similar problem, but it's different. It's how many ways are there to write p to the k as in this form, okay? And there's a lower bound for the number of those things, and so due to work of Eichler and Igusa, which is a proof of one of Ramanujan's conjectures, okay? So anyway, basically these were based on number theory. And they sort of left open the question, which was asked by Lubatsky, which is what happens for other d, right? So well, I just told you that if d is equal to prime plus 1, then this number theory thing gives you these optimal graphs. Well, what happens for other d, right? So the conceptual content of this question is the existence of Ramanujan graphs, is it a number theoretic phenomenon, or is it a more generic, like graph theoretic phenomenon, right? So until recently, the only Ramanujan graphs known were these, and what we proved is that in the bipartite case, there are infinite families of Ramanujan graphs for every d. Okay, So which don't have to be prime or anything like that.
Not coming from number theory.
Yeah, and not coming from number theory. Very elementary. I'll show you the whole proof in this talk. Okay, so proof is completely elementary. It does not use number theory, and you could probably understand it in high school or something like that. But there are some caveats. So it's not explicit. It's just an existence proof. So the previous thing were very explicit Cayley graphs of some groups, right, with some generators. This is not explicit. This just proves that they exist. And it's based on this new method that we developed called the interlacing families, which I'll describe in a moment. Okay? So any questions about the result? Remember that bipartite means that you have a d and a minus d, and you're interested in everything else being at most 2 square root d minus 1. Okay, so how do we do this? So we followed an approach suggested by Bilou and Lineal in 2006. So the goal is you're given a d, right? So d is the degree. Maybe it's 3 or something, or 5 or whatever, right? And you want to construct an infinite sequence of d regular graphs with small eigenvalues. So one way to do this would be to find some operation which doubles the size of a graph without blowing up its eigenvalues. Okay? So what I would like to happen is sort of shown in this picture. Suppose I have a d-regular graph on n vertices with some eigenvalues, and say it's already Ramanujan. So these eigenvalues, these blue circles, already lie in this interval, right? Well, okay. Suppose I find some operation which turns this into a graph on 2n vertices. So it makes it twice as big, right? Then, well, that's going to have 2n eigenvalues, right? So they may not, there may be some new eigenvalues, right? The eigenvalues, there will be more of them, and they may be different. But suppose I can find an operation which does this and guarantees that all the new eigenvalues are still Ramanujan, right? So if I prove that for every Ramanujan graph, there's a graph of twice as many vertices with the same bound, then I just repeat this infinitely many times, and you get the infinite sequence, right? Okay. So Bilou and Lineal suggested a very natural, sort of nice operation for doing this, and it's called a two-lift of a graph. Okay. So it's also called a two-cover. It's a topological notion if you're familiar with that. But let me just define what a two-lift is. So suppose I have a graph, a d-regular graph on n vertices. In this case, n is 5. I'm going to call this this is not regular, okay, but suppose I have a d-regular graph on n vertices. I'm going to call this the base graph, okay? And this is the graph that I would like to double. So here's how I construct a two-lift of the graph. So first I make 2 copies of the graph. So now automatically I get a graph on 2n vertices, which is just 2 disjoint copies of this. And for every vertex, there are 2 copies, a0 and a1. All right? Okay. And now for every edge in the original graph, there are 2 parallel edges, right? So for this edge c0, d0, for the edge cd, there's c0, d0, and c1, d1. Okay. And now for each of these pairs of edges, I'm going to make a decision. I'm going to either leave it as it is, or I'm going to cross it. Okay. So if there are m edges in the graph, I just look at every edge, like say cd. I either leave it as c0, d0, c1, d1, or I make it c0, d1, d0, c1. So just cross or parallel. And there are m edges, and I do this for every edge. Some of them I leave, some of them I cross. And there are 2 to the m possibilities, right? Because for every edge I have 2 options, and there are m edges. So every graph has 2 to the m2 lifts. And each of them is a graph, which is, you can easily check, is also d-regular if the base graph was, and has 2n vertices. So the nice thing about two-lifts is that what a two-lift does to the eigenvalues is very structured, and sort of there's a very clean characterization of it. So let's look at what taking a two-lift does to the adjacency matrix of a graph, right? So here's a base graph. It has n eigenvalues, lambda 1 through lambda n, and that's its adjacency matrix. So when I do the two-lift, first I make 2 copies of the graph, right? So this is the new adjacency matrix. It is just 2 copies of the old one with zeros on the off diagonal. And now you can easily see that each time I cross an edge, I move the entries onto the off diagonal block. That's what crossing an edge means. Okay. So this is just 2 copies of the original graph. I want to cross this edge. I move these entries to the off diagonal. I make these 0 and move them to the off diagonal. Okay. You can just check. This is literally the adjacency matrix of the two-lift. And this is a 2n by 2n matrix, and so it has 2n eigenvalues, right? Now, the first very nice thing that happens is it's an easy linear algebra exercise to see that n of the eigenvalues are the same as the old eigenvalues. So a priori, this could have 2n arbitrary eigenvalues, but that doesn't happen. n of the new eigenvalues are just literally the old eigenvalues, lambda 1 through lambda n. Okay? And then there are some n new eigenvalues I'm going to call lambda 1 prime through lambda n prime. Okay. And what I'm interested in is what are these lambda 1 prime, right? I want to find a lift so that these are also, you know, Ramanujan or something of that nature. Okay, so it gets even better. So there's this very nice way of reasoning about what the new eigenvalues are. So to do that, I'm going to define an auxiliary matrix called the signed adjacency matrix of a lift. Okay. So a graph is an adjacency matrix. For a two lift, for each edge, I do either parallel or cross, right? So I'm going to do is I'm just going to write down the adjacency matrix of the graph. For the edges that I crossed, I'm going to replace the ones by minus ones. Okay? And for the edges that I left, I'm just going to leave them as ones. So this is called a signing of an adjacency matrix. It's a pretty natural thing to do. You just set some of the signs to minus 1. And you know, this is exactly the same thing as a lift, because for each lift you just make a binary decision. So it's just a different way of representing a lift as a signing. Okay. Are there any questions about what this is?
So earlier you represented it as a 2n by 2n.
Yeah, this is n by n. Yeah. Yeah. I mean, in the end, a lift is just it's just a bit string of length m, right? Because for every edge I just decide cross or parallel. This is a particular representation of the lift, right? I just write down the adjacency matrix, and for every edge that I cross, I make it a minus 1. Okay, and then the nice theorem, which is a linear algebra exercise that you can do, is that the new eigenvalues are just literally the eigenvalues of the signing. Okay, so what a lift does to the eigenvalues is completely encapsulated in this matrix. Okay.
Simple to do.
Yeah, 3 lines or something. Yeah, it's a nice exercise. You can prove it if you want. Okay. So what that means is that a lift is the same thing as a signing, and the eigenvalues are literally the eigenvalues of the signing. So the problem of finding a good lift literally is the same as the problem of finding a good signing. Okay? So the conjecture was every d-regular graph has a 2. So they made this very bold conjecture. Every d-regular graph has a 2 lift in which the new eigenvalues are at most 2 square root d minus 1, which in the language of signings is literally just this statement. Every d-regular adjacency matrix A has a signing such that the norm of the signing is at most 2 square root d minus 1. The norm of a symmetric matrix is the largest absolute value of its eigenvalues. Okay? So this is just a question about matrices. I give you a 0, 1 matrix. I want you to flip some of the signs so that the norm of the thing that you get is at most 2 square root d minus 1. That's the problem. So this is what they conjectured, and we proved this conjecture in the bipartite case. So what we proved is that every d-regular adjacency matrix A has a signing, so the largest eigenvalue of A of the signing, A sub s, is at most 2 square root d minus 1. So this does not say anything about the least eigenvalue, right? The norm is the largest absolute value. We just get the max of the eigenvalues. So we only get one end of the spectrum. But then we use this trick, which is this fact that I mentioned earlier, that if the graph is bipartite, the eigenvalues are symmetric about 0. Right? So certainly if you bound the largest eigenvalue, you automatically get the bottom one for free. This is the only place bipartiteness comes in the proof. Okay. So this is what we prove. Okay. So are there any questions about this statement? It's a very concrete thing. Like you give me a d.
What could be the general matrix like zeros, ones, minus ones, and number of minus ones d1? The signing of a d regular.
Yeah. The signing is literally anything like this, right?
Captured is number of minus ones e1 symmetrically.
Yeah, so the number of minus 1s is symmetrically placed. That's the only thing, yeah. It's just, you just give me a d-regular adjacency matrix and ask me to flip some of the signs symmetrically, yeah. Okay. So how do we prove this theorem? Okay, so there are several things you could try, right? So what you have to find is the signing. So one reasonable idea is to choose a random signing, right? So for every edge, just randomly cross it or keep it parallel. What that means is for every entry in this adjacency matrix, make it randomly +1 or -1 probability. Okay, so this is it's not a very bad idea, but it doesn't actually solve the problem completely. So what ends up happening is when you do this, the expected norm of the thing that you get, you can check can be much bigger than 2 square root d minus 1. Okay, so in expectation it doesn't work, but it's not insanely bigger. So what Bilo and Lineal proved is that when the base graph is Ramanujan, this is at most order square root d log cube d. Okay, which is not that bad. So remember that the eigenvalues can lie between 0 and d. Square root d is much smaller than d. Square root d log cube d still sort of okay for big D. Okay, So it's not awful, but it doesn't get you this 2 square root d minus 1, which is the.
What do you mean by A is nearly Ramanujan?
Yeah, so that's something they defined. I think they defined it as being anything whose eigenvalues are at most this number. So it's not 2 square root d minus 1, it's order square root d polylog d. Okay. Okay, so the main idea in this work is to do the following. So first we make this sort of change of notation. So observe, we're interested in controlling the eigenvalues of a matrix, right? So the eigenvalues of a matrix are just the roots of its characteristic polynomial. That's just linear algebra fact, right? So the characteristic polynomial of a sub s, which is the signing of a, I'm going to denote as chi of a sub s, and that's just determinant of xi minus a sub s, right? And the roots of that are literally the eigenvalues, and I'm interested in the largest root. So I want to prove that there exists a signing so that the largest root of chi of a sub s is at most 2 square root d minus 1. I mean, I haven't done anything, I've just changed notation. Okay, so the main idea is to consider this object. It's the expected characteristic polynomial over a random signing. Okay, so there are 2 to the m signings. For each signing there's a polynomial, right? I'm literally going to average all of them. Okay, so it's a little funny because when you average polynomials, you average their coefficients, right? By average, I mean just add them, literally. And so, I'm interested in the zeros of the polynomials. I'm not interested in the coefficients, right? But nonetheless, I'm going to average the coefficients. Okay. Okay, so usually this is a useless thing to do because you can averaging polynomials can do all kinds of crazy things to the roots, and in general, there's very little that can be said about it. But it turns out in this case, these polynomials have a special property, which I will discuss in detail, which implies the following statement: there must exist a signing s, so that the largest root of chi of a sub s, the largest root of that polynomial, is at most the largest root of the expected characteristic polynomial. Okay? So basically, you're able to relate the existence of one polynomial to the roots of an average polynomial, which is which is a different kind of object. Okay, so given that this is what I'm going to do, there's a clear proof strategy. So first is to prove what I just claimed. Prove that there exists one polynomial, one signing s, so the largest root is at most largest root of the expected polynomial. And I just want to reiterate that this is very different from the usual averaging arguments, where you say that there exists one polynomial, so the largest root is at most the expected largest root. This is a trivial statement about averaging numbers, right? What I've done here is put the expectation inside the largest root function. Okay, so the whole content is that I'm able to average coefficients and reason about roots. It would be easy if I could average, I mean, this is a trivial statement, but as I already told you, the average root is actually bigger than 2 square root d minus 1. Okay. Okay, so first prove this. Second is calculate the expected characteristic polynomial. Okay. This turns out to be a known object from statistical physics called the matching polynomial. Okay. And the third step is to bound the roots of the expected polynomial, which turns out to be 2 square root d minus 1. Okay. So if you put these 3 things together, it proves the theorem. Right? But somehow the key is that this this analysis is being done on this average polynomial object, not on particular instances of the problem. And then that'll finish the proof. Okay, so let me start with the second and third parts to sort of motivate the first part.
So
and
existential, not constructive.
Existential, not constructive, yeah. So let's do this part. Okay, so this was actually done over 30 years ago by Godsell and Gutman in a different context. And they proved this identity, which says that if you have any graph G, and you look at a random signing of it, then the expected characteristic polynomial of a random signing is equal to the matching polynomial of the graph. Okay. Okay. What's the matching polynomial of a graph? It's something that was defined by Heilman and Lieb in 1972 in this monomer-dimer models in statistical physics. So it's basically a generating function which counts the number of matchings of different sizes in a graph. Okay. So if you have a graph with n vertices, then the matching polynomial is a degree n polynomial, and the coefficient of x to the n minus 2i is the number of matchings of size I. Okay. So here's an example. Here's a graph, and here's its matching polynomial. There is 1 matching with 0 edges. This is the convention. Okay. There are 7 matchings with 1 edge. So matching with 1 edge is just an edge, right? And then there turns out there are 11 matchings with 2 edges. This is what they are. Okay. And then there are 2 matchings with 3 edges, which are perfect matchings. Okay. So this polynomial is a generating function which just counts the numbers of matchings of different sizes. Okay. So here's a proof that these things are equal, which is, I don't think it's the original proof, but it's an easy proof. So the proof is, just expand this using permutations, right? So what's the determinant? It's a sum over all permutations of the sign of the permutation times the product of terms, in the matrix. So determinant is the sum of permutations, and what does this matrix whose determinant I'm taking look like? It's xi minus a sub s, where a sub s is a signing, and a sub s is a random matrix, right? Because each of these signs is randomly plus or minus 1. So it's a matrix with x's on the diagonal and random plus minus 1 is on the off diagonal. Okay. But of course, because the signing is symmetric, for each edge you choose the same sign. You don't just flip each entry randomly. Okay. So let's see what happens, right? So here's a permutation. If the permutation hits any zeros, you get 0, right? It's a product of terms. If any of them is 0, you get 0. And if you choose just 1 entry for any edge, you also get 0, because these edges are independent, right? The signs on the edges are independent. So if you choose, so by independence, the expectation of the product is the product of the expectations for these independent edges, and the expectation of this is 0. Okay. So any permutation that shows up in the sum has to pick both copies of an edge. Okay. And now, well, it's easy to see the only permutations that do that are involutions. Okay. The only permutations that map the only permutations that count map I to j and j to I, which is a swap, right? Those are matchings, right? That's what they are. So either you pick some guys on the diagonal, or you pick a bunch of swaps. And so the only terms that show up in the sum are matchings, and then you just write it down and you get the matching polynomial. Okay. So it's like a 4-line proof. Okay. Are there any questions about this proof? Okay. Okay. So that's done. The expected polynomial is the matching polynomial. And okay, now what about this? What can we say about this matching polynomial? This was done 40 years ago in the original work of Heilman and Lieb in 1972. So they proved a bunch of stuff about this. So first they proved that all the roots are real, which is not a priori at all obvious, right? If I just write down a polynomial, the roots can be anything. They proved that the roots are real, and they proved that there are absolute values at most 2 squared t minus 1. Okay, so this number has a meaning. This number is the spectral radius of the infinite deregular tree, if you know what that is. This is the same object that's used to prove the lower bound of Alon and Bopana. Okay, so this number, it's not a coincidence that the same number appears in both places. The number literally comes from the same object, which is an infinite deregular tree. Okay, the proof of this is also about half a page. It's based on some combinatorial recurrences. You just write down the polynomial and see what happens when you delete a vertex, and you get some recurrences and solve them. This requires more cleverness than what I showed you on the previous slide, which is just follow your nose. But nonetheless, it's elementary. It doesn't use number theory or anything like that. Okay, so that's done, right? So we know that the expected polynomial is great, 2 squared t minus 1. So now all we have to prove is the first part. And this is implied by a structural property of these polynomials that we call interlacing family. Okay, so but basically, okay, what are we trying to do here, right? We're trying to say that there's a bunch of polynomials, and when you average them, the roots of the individuals are related to the roots of the sum in some way, right? So let's first try to understand the simplest case of this problem, which is when you have 2 polynomials. Okay, so here you have 2 to the m polynomials. Let's just see what happens for 2 polynomials, right? So here's the basic question. Suppose you have 2 polynomials p0 and p1, which have real roots, and they have the same degree. When are the roots of the individual polynomials related to the roots of the average polynomial? Okay, so the average polynomial obtained by averaging the coefficients. I want to say that the roots of the average are somehow averages of the individual averages of the roots of the individuals. Okay, that would be the ideal statement. If everything was linear, that would be true, but it's not. Okay, so when does this happen? So it doesn't always happen. So here's a canonical bad example. Okay, the two polynomials are x minus 1 squared and x plus 1 squared. So they're quadratic polynomials, and they have roots at minus 1 and plus 1. But when you add them, you get something that's a sum of squares. So it's strictly positive, right? So the roots of the average polynomial are actually not even real. Okay. I mean, you know, you can just check that the average of these two polynomials is x squared plus 1. So the roots are I and minus I. So, okay. So averaging polynomials doesn't even preserve real roots, let alone saying anything nice about their locations. And most of the time, this is what happens. This is not a degenerate instance. If you pick two random polynomials, this is what will happen. You'll get some very weird behavioral roots. But sometimes something very nice happens. So here's an example where something nice happens. If I move these two quadratics, so the roots alternate, like in this picture. Okay. So suppose I have roots 1, 3, and 2, 4. Then you can check that the average polynomial looks like that. It has real roots, and the roots of the average are actually averages of the original roots. I mean, not uniform averages, but the roots of the individual of the average lie in the convex hollow of the corresponding roots of the individual polynomials. Okay. Okay. So this is also not an isolated incident. So it turns out that this happens. That there's a clean sufficient condition which characterizes when this happens, and this is what we use. So so you know, the characterization of when this stuff is really well behaved is given by this property called common interlacing. Okay. Okay. So what's an interlacing? So suppose I have a polynomial q of degree n minus 1 with roots alpha I, and a polynomial p with roots beta I. Then I'm going to say q interlaces p if the roots look like this. So between every two roots of p, there is a root of q. So they alternate. The roots alternate, like in this picture. So this interlacing itself is, of course, it's a hundreds of years old notion. But what I'm going to now say is that two polynomials have a common interlacing if there's a third polynomial that interlaces both of them.
The degrees should be like that, one less than the other.
I mean, yeah, the way I've defined it here is fine, but you can also define it for two polynomials of the same degree. Then you have one more root here or at the bottom. But yeah, basically alternation is the main thing. Okay. Okay. So common interlacing just means that there's a third polynomial that interlaces both the polynomials. And the main theorem that we prove about this is the following. If you have two polynomials that have a common interlacing, p0 and p1, real roots, same degree, and they're monic, that's important. So the first term is just x to the n. Then there exists an I, so the largest root of pi is at most the largest root of the average. Okay? Okay, and the proof of this is very easy. I'll just show it to you on this slide. So here's the proof. So I'll just show it to you by picture. Okay? So here are two degree 3 polynomials that are monic and have real roots, p0 and p1, right? So they have a common interlacing. The common interlacing is a quadratic polynomial with some roots alpha I, and the common interlacing roots look like this. Between every two roots of the red polynomial, there's this alpha, and between every two roots of the blue polynomial also. This is what common interlacing looks like. Okay? And now the roots of this common interlacing split the real line into three intervals, right? There's the one before alpha 1, there's alpha 1 to alpha 2, and there's alpha 2 to infinity. And by the definition of interlacing, each of these intervals contains precisely one root of each of my polynomials, right? Okay, so now I'm gonna look at these intervals. So I have these closed intervals that are intersected at most one point. I have these three intervals. Each one contains exactly one root of each of my polynomials. Okay, that's the property I'm going to use. So let's look at the last interval here, right? So observe that because the polynomials are monic, at infinity they're both positive, right? So to the right of this interval, each polynomial is positive. So the average is also positive, right? However, I know that inside this interval, each polynomial changes sign exactly once. So at the beginning, each polynomial is non-positive because it changed sign exactly once, right? Therefore, the average is also non-positive. But then the average went from being non-positive to being positive, so it has to be 0 somewhere. And that's it. So that means that I can take this interval right up against the roots of these two polynomials, and I just proved that the average has a root somewhere in between them. So that's it. It's just a intermediate value theorem. So are there any questions about this? So this seems completely trivial, but this is actually the whole technique. So are there any questions about this proof? Basically, this common interlacing makes sure that these roots, the largest roots don't interfere with the second largest roots, don't interfere with the third largest roots, and you get these intervals when everything just behaves, as you would expect. Okay. Excuse me?
All matching polynomials.
So this is a property, as I've defined it, this is a property of two polynomials, right? This is a property of pairs of polynomials. So what do you mean by it does a matching polynomial have this property?
Earlier you were telling matching polynomials.
Yeah.
So matching polynomials have this property?
Well, this property is defined for a pair of polynomials, right?
That's one polynomial.
The matching polynomial is one polynomial, right? So are you asking if two different matching polynomials? No, they don't. They don't. But there are some related polynomials which I'll tell you about that have this property, which is what we use. Okay. So yeah, so that's it, right? So therefore, because the average has some 0 in this interval, it's at least the minimum of the largest roots. Okay, so what's an interlacing family? An interlacing family, so this showed you how to do the argument for two polynomials, right? But I want to do the argument for 2 to the m polynomials. Interlacing family is just a way of applying this observation inductively. So suppose I have a family of polynomials p sub s indexed by 0, 1 to the m. So I have 2 to the m polynomials, as in my situation of interest. So it's called an interlacing family if there is a binary tree, a complete binary tree, such that the polynomials are at the leaves of the tree, okay? And at each internal node, I'm going to define a polynomial which is the sum of its children, okay? So the leaves are just p naught naught, p naught 1, p1 naught, p1 1. The nodes above that are just going to be the averages of the subtrees, okay? So I'm just going to do this very natural thing, okay? I'm going to define this tree, and at each node there's a polynomial, and the polynomial is the average of all the polynomials under it. It's an interlacing family if you can make this tree, and it has the property that each pair of siblings at every level, okay, has a common interlacing. So common interlacing is what I told you on the previous slide for how to solve this for two polynomials. Here I'm saying that for any internal node, if you look at the two children, they have a common interlacing. That's an interlacing family. Okay. Okay, so the sort of very immediate theorem about this is that if something is an interlacing family, there exists an S, so the largest root of p sub s is at most the largest root of, the polynomial at the root of the tree. And the proof is just induction, right? So you start at the root, you look, so p of nothing is the average of all of the polynomials, right? It's a sum of p naught and p1. Right? P naught is the sum of all polynomials with a 0 in the first bit. P1 is the sum of all polynomials with a 1. But these have a common interlacing. So the largest root of one of them, say p naught, is at most the largest root of the root. Okay, but now you just do it again, right? So you just keep doing this. You just follow it down the tree. And that's it.
What you do for two polynomials, you just keep...
Yeah, you just do it inductively for 2 to the m polynomials by basically looking at, what are these? These are conditional expectation polynomials. So these are the polynomials you're interested in. This is the expectation of all of them. But the internal nodes correspond to conditional expectations. That if you fix the first bit and average over the rest, you get this polynomial. So all I'm doing is just, in computer science, this is called the method of pessimistic estimators. It's just, you just look at the conditional expectations and just follow the ones where the probabilities are. Okay. Except we're not looking at probabilities here, we're looking at roots. So, okay, but basically just induction. Okay, so the main theorem is that now getting back to our actual situation, if you write down the polynomials, excuse me? Yeah, if you write down the polynomials corresponding to signings of an adjacency matrix, it's an interlacing family. Okay? And remember, these are determinants of x minus a sub s, right? Okay. So how do I do that? So how do I prove that something is an interlacing family, right? So I need to prove a bunch of common interlacing statements, right? One for every internal node of this tree. And how do I prove common interlacing statements? So one way is to just produce the common interlacing, right? Just produce it somehow cleverly, okay? But fortunately, there's a very nice characterization of when two polynomials have a common interlacing. So this has been around since at least 1980. It's a folklore sort of lemma, but it appears in the book of Fisk. And the lemma is this, that two polynomials have a common interlacing, two polynomials with all real roots have a common interlacing if and only if all their convex combinations have real roots. Okay? So, I mean, this is an exact characterization of when a common interlacing exists. This has a 3-line proof that you can find. It's a nice exercise, but it's actually very powerful because it turns this existential statement about existence of a common interlacing into a for-all statement, but verifying real rootedness of all convex combinations. So now you don't need any cleverness to do this. You just have to check this condition. Okay? And yeah, this is a nice exercise which you can try to do. Okay, so this is the characterization I'm going to use to prove that the thing is an interlacing family. Okay, so let's write down the tree for our thing that we're interested in. So again, you know, the tree, the leaves are indexed by signings, which I'm going to call a signing S1 through Sm. There are M signs, one for every edge. There are M edges. The leaves are just signings. The internal nodes are partial signings, S1 through Sk. So I'm going to fix the first K signs and let the rest of them be random. And then the internal polynomials, as I mentioned, are just conditional expectations. They're expected polynomials when you fix the first K signs. So I need to prove that you know, for every internal node, the two offspring have a common interlacing, right? So let's just pick some S1 through Sk, and I need to show that it's two extensions. So it has two extensions. It has S1 through Sk1 and S1 through Sk minus 1, right? So it has two children. I need to show that they have a common interlacing, which by the lemma I mentioned is equivalent to showing that all convex combinations are real rooted, right? Now I'm going to observe that any such polynomial is an expected characteristic polynomial over all the signings, but with a biased distribution. Okay? So initially the distribution was uniform, right? You pick every sign with probability half plus probability half minus independently. But now here I fixed the first S1 through Sk. The K plus first sign is now going to be 1 with probability lambda and minus 1 with probability 1 minus lambda. And the remaining are still random, right? But now the point is this is actually an average over all the polynomials, but with these biased probabilities. So for S1, the probability distribution is going to be deterministic. It's just going to pick S1. That is still a probability distribution. And so for the first K, it's going to be deterministic. For the K plus first, it's going to be biased with this parameter lambda, and for the remaining, it's going to be uniform. Okay. So why am I doing this? Well, you know, once you write it this way, you see that existence of all the common interlacings you need is actually encapsulated by this very concise statement that the expected polynomial is real rooted for every product distribution. Okay. So previously I said all these things about internal nodes and leaves and like trees and stuff. All of these interlacings, because of this characterization, are guaranteed by the following statement that if you have a family of real rooted polynomials indexed by, you know, plus minus 1 to the m, it's an interlacing family if it's real rooted for every product distribution. Product distribution means for every sign, you choose it with some bias, which may be different, but they're independent. Okay? The key is independence. And this can be seen as a generalization of Heilman and Lieb, right? So Heilman and Lieb showed that when you take the average, when this is a uniform distribution, you get the matching polynomial. And they proved that that has real roots, right? Now I need to prove that for any product distribution, this has real roots. So you can use it as a generalized matching polynomial. Okay, so I need to prove this. Okay, so are there any questions about this statement? Okay, but you can just view it as a generalization of the matching polynomial. Okay, so what do I need to do? I need to show that the expectation of you know, P sub s, where P sub s is actually the characteristic polynomial assigning s, is real rooted. So first I'm going to observe that real rootedness doesn't change if you shift the variable by a constant. If you take a polynomial in x and you make it a polynomial in x minus d, the roots are just shifted by d. So it suffices to show that the expected polynomial, the expectation of P sub s x minus d has real roots for every product distribution on s. And that is something that looks like this. Determinant of xi minus di minus a sub s, right? Because I just threw in this di here. Okay, why is this useful? Why am I doing this? Well, if you write down a sub s, right, as a function of the signs, so for every edge ij you have a sign sij, and that appears in two entries, ij and ji. So you can write a sub s as a sum over ij edges sij times a rank 2 matrix, delta I delta j transpose plus delta j delta I transpose. This is just a matrix with two entries in ij and ji, right? So you can write it as a sum of rank 2 matrices, okay, where it's plus if it's a, you know, you just flip the sign of these matrices depending on the sign. It turns out when I shift everything by d, I get this, okay? D minus a sub s, where a sub s is assigning, can be written as a sum of rank 1 matrices. Okay? So for every edge ij, I now have a rank 1 matrix, which is either delta I minus delta j transpose, or delta I plus delta j plus delta j transpose. And for the places where I take a sign of 1, I put this matrix, and when sign minus 1, I put this matrix. Okay? So, you know, for the uniform distribution, for every edge, I pick this with probability half and this with probability half, and I just add them. Okay? Okay, so this is similar to what you do when you turn an adjacency matrix into a Laplacian matrix. So if all the signs are 1, this is just the adjacency matrix, and this is just the Laplacian matrix. So you can think of this as a signed Laplacian matrix, if you know what that is. But anyway, the whole point is I've converted something that's a sum of rank 2 matrices into a sum of rank 1 matrices. Okay? Okay, this is very important, because now I can write this polynomial I'm interested in, expected determinant of xi minus di minus a sub s, as an expected characteristic polynomial of a sum of independent rank 1 matrices. So for every edge ij, I define, well, a random vector vi red, which is going to be delta I minus delta j with probability whatever the bias is, and plus with some other probability. And I look at vij transpose a rank 1 matrix. But the point is, I've written my polynomial as an expected characteristic polynomial of a sum of independent rank 1 matrices. Okay? Okay. And now we have this master theorem, which is all such polynomials have real roots. Okay, so even more general theorem. Any independent random vector is v1 through vm red. Okay, so independent random vector means vi is a random variable that takes values in Rd, let's say, and they're independent. The distributions are independent, but they're not the same. Given any independent random vectors v1 through vm red, their expected characteristic polynomial has real roots. Okay, and clearly a special case of this is shifting of the expected expected characteristic polynomial with signing. Okay, so how do you prove that? So, okay, are there any questions? So several people look confused actually, or I don't know. Okay, this is just a more general case of what I want to prove. Okay, and what I've done is I've changed the variables to get this rank 1 structure. And the conceptual point here is that interlacing happens because there are some rank 1 matrices hidden in there somewhere. Okay. So if you may know Cauchy's interlacing theorem. So it really is, interlacing comes from rank 1 matrices. That's where it comes from. Okay. So but how would you prove something like this, right? So given such independent random vectors, how do you prove these have real roots? So then there's this philosophy that has been sort of around in statistical physics for several decades. Which is, if you want to prove that a polynomial has real roots, you should not attempt to do it directly. Because basically, if you look at the space of univariate real-rooted polynomials, the set of transformations between them is somehow not rich enough. I mean, this is a heuristic statement, but it's difficult to prove univariate real-rooted statements. And so what Alan Sokal, for example, suggested is that what you should do is instead you should view your univariate polynomial as a restriction of some multivariate polynomial. And you should prove that the multivariate polynomial has real roots, whatever that means, which I'll tell you in a moment. And then, this has been used a lot by Rhoda and Borchea and Brandon recently, and this is sort of a general philosophy of how to prove real rootless results. Okay. Okay, so what's a multivariate real-rooted polynomial? It's called a real stable polynomial. Okay. So a polynomial p with real coefficients in variables z1 through zn is real stable if whenever you plug in zi in the upper half plane, strictly in the upper half plane, okay, imaginary part strictly greater than 0, it's non-zero. So it has no zeros with all entries strictly in the upper half plane. That's a real stable polynomial. Okay, so the first thing to observe is that a univariate real stable polynomial is the same thing as a real rooted polynomial. Because in the univariate case, roots occur in conjugate pairs, right? So if you don't have any roots in the upper half plane, you don't have any in the lower half plane either. Okay, so the 1D case of this is real rootedness. So it's a generalization of real rootedness. And you know, the sort of really amazing thing about these polynomials, so this is a pretty strong property, but it's closed under all kinds of crazy operations, which are very well understood. Okay, so here are two of the most basic closure properties, which we will use. The first is if you take a real stable polynomial and plug a real number into any one of the coordinates, you get a polynomial in n-1 variables. That's also real stable. Okay. The second, which is so this is easy to prove. If you know complex analysis, this is like 2 or 3 lines. The second one is that if you take p and you do p minus the derivative of p in any of its variables, so this is I minus partial zi applied to p, this is also real stable. Okay. So this also is about 3 lines, and it's similar to the proof of the Gauss-Lucas theorem, which says that if you take a polynomial and compute its derivative, that also has real roots. And so this was actually proven by Lieb and Sokal in 1981. Same Lieb from Heilmann-Lieb. But anyway, these are both actually easy to prove, and the thing that's all we're going to use, but there's a huge list of these transformations, and in fact there's a full characterization of linear transformations preserving real stability. So this is a very safe area to be in. Like, you don't need to be clever. You just it's very systematic. Okay. Okay. So I just told you that there are some closure properties, but I need to start with something that's real stable, right? And there's sort of a very canonical real stable polynomial that you always start with in these proofs. Okay. And this also must have been around for several decades, but the place where I've seen it written down is Borchea and Brandon. It says if you have positive semi-infinite matrices A1 through AK, so these are matrices all of whose eigenvalues are non-negative, then determinant of some Zi AI is real stable. Okay. This has a 3-line proof, which is based on the fact that the eigenvalues of a symmetric matrix are real. Okay, so this is also, if you're interested in this, I encourage you to prove this and these as exercises. But this is quite easy. Okay, so that's all I'm going to use. Okay. And the plan is to use these 3 facts to prove that that is real stable. The expected characteristic polynomial is sum of independent rank 1 random matrices. Okay. So the entire proof comes down to proving this identity, okay, which I'm going to call the central identity in this work because it reveals all of the structure that's used about these polynomials. Okay. So here's the identity. It says that if you have v1 through vm independent random vectors, then the expected characteristic polynomial sum vi transpose is equal to that. Okay, so this is a univariate polynomial. It's a sum of 2 to the m polynomials. I mean, sum of maybe exponentially many polynomials. What is this? This is a determinant of xi plus some zi ai. So zi are some additional variables. There are m of them. Ai are the covariance matrices of these vectors vi. Okay. So this is some sort of multivariate characteristic polynomial type of thing. These are a bunch of differential operators. So for every I apply I minus differentiation with respect to zi, and I do it for all of them. So when I apply these to this polynomial, I get another multivariate polynomial, which with m plus 1 variables. But then I set all the new variables to 0. Okay. Okay. So this identity, you know, what it tells you is that adding independent random rank 1 matrices is the same thing as applying differential operators. Okay. And rank 1 and independent are critical here. If you drop any one of those things, nothing like this is true. Okay. Another way to view it is that this is an expectation of a determinant. Here I've taken the expectation inside. This AI, the expectation went inside the AI. Okay. Okay, so once you decide to prove this, it's also easy to prove. You can prove it in half a page using Cauchy-Binet or any kind of linear algebra, whatever you want. Okay, but this is it, right? So once you have this, the proof is essentially immediate. So this is real stable because it's a sum of, so xi, I is positive semi-definite. Any covariance matrix is positive semi-definite. So this is real stable. These operators preserve real stability, and setting variables to 0 preserves real stability. So this whole thing is real stable, but then that's real stable, but that's univariate, so it's real rooted. Okay. So just the existence of this formula is the proof, basically. So are there any questions about this?
How do you think that, how do you map that rank 1 matrices to covariance?
Yeah, so you have to, well, I haven't actually proven this to you. You have to expand this in a particular way, and you know, but I mean, okay, there is a very simple fact at the bottom of this, which is if you write down determinant of a sum of rank 1 matrices, it's multilinear in the rank 1 matrices. It comes down to the fact that determinant is multilinear in each one of its columns. That's all this is, actually. Okay. Well, no, the PSD is required in the real stability part. This is true anyway. Well, I mean, okay, I mean, there's an implicit PSD in here. This is always PSD, right? But yeah, the fact at the bottom of this is determinant is multilinear. That's it, and it fails to be multilinear when you look at 2 columns, right? So that's where the rank 1 comes in. Anyway, so once you have this, you're done, right? So I just proved that all expected characteristic polynomials of sums of independent rank 1 matrices are real rooted. Special case of this is expected characteristic polynomial of assigning under any product distribution shifted by D, which does obviously the same thing as if I just shifted back, which then implies that this thing is an interlacing family, because all those common interlacings exist, which then implies that there exists assigning, which does as well as the average, which then proves the existence of a good lift, you know, this thing, and then that's it. That's the whole proof. So yeah, okay. What's the main theme here? So you know, I think one interesting thing about this work is that there are 2 very distinct parts of this argument. So the first is you reduce this existence statement, this, you know, hard problem of finding the signing, to proving real rootedness of a bunch of polynomials, right? So you'll notice that the place where the existential quantifier disappeared is in that lemma. It turned from an existential statement into a for all statement, right? So you reduce this existence to proving a bunch of real rootedness statements. But then you're not done. You do need to analyze the roots of the polynomial that you get. And that is done in a completely modular way by completely different means, you know, whatever you want. So in this case, we did the first part using completely generic techniques, using real stability. The second part, we did it using very specific techniques. The first part works for any sums of independent rank 1 matrices, right? The second part is very specific for matching polynomials and graphs, because the proof of this bound is based on combinatorics. But it turns out you can actually do the second part also completely generally. So this is something we did in another paper, and you can use it to prove a bunch of other stuff, including this thing called the Katzen-Singer conjecture. But the nice thing is these things are completely disjoint, and you can do them really separately. So that's it. Yeah.
So non-bipartite graph, how's the positive I can find?
So I mean, what we get is that the largest eigenvalue is at most 2 square root d minus 1, right? Yeah. No, this does give that, but it doesn't tell you anything about the smallest one.
So negative it can be.
Yeah, so negative it can be. So that's actually still open. Well, okay, what's not open is we know how to prove 4 square root d minus 1, but 2 square root d minus 1 is open. Yeah. Yeah. Yes?
Do these methods exist to proving results about the kth eigenvalue?
Yeah, they do, actually. So all of this stuff, I mean, you know, in this picture that I showed you, right, I didn't actually use anything special about the largest eigenvalue. I could do it for the 3rd eigenvalue. I could do it for the 10th eigenvalue. So the problem is you can only do 1 eigenvalue at a time. That's the, but yeah, there are other applications where one is interested in lower bounding the kth eigenvalue. Upper also is not a real thing here. Yeah. So yeah, so I guess one of the interesting open questions from a computer science point of view is this is not an algorithm, right? So to actually construct this, you need to compute these polynomials, and as I told you, the last coefficient of the matching polynomial counts the number of matchings. which is sharply hard. So there's a question. Can you turn this into an algorithm?
Any connection with the upper bound conjecture between roots of polynomials and sum of the roots of polynomials? Matrices.
Excuse me?
Upper bound conjecture of the matrices. Eigenvalues of A and B.
What is the upper bound conjecture?
Eigenvalues of A and B related to eigenvalues of A plus B.
You mean like this honeycomb conjecture kind of stuff? Or?
The 80s.
Yeah, so my understanding is that attempts to understand what happens in the case when A and B are both arbitrarily high rank. So I think this is much more special than that, because the rank 1 stuff is really crucial here. So we don't yet know any place where this stuff works when things have really high rank. You have to be able to break it down into small rank 1